Hello everyone. So today we're going to continue where we finished last time, which is lesson 2E. So we did lesson 2E, okay? I have a note here, English version did the last example, which is 2E. So now we continue with this example here. And he continues to expand, okay, about the addressing mode, basically. So if I start going through my notes, okay, so I'm going to cover what is highlighted in blue. And here he gives lots of examples to make you aware of what the more options related to this instruction, so that you don't get because beginners get confused quite easily. So yeah. So the first one is move long 80 to D0. So the first one, we move what's in 80 to D0, basically. The second one, and it's a move long, the second one, move dot byte. So we move the byte that is at address 80 into the 0. Okay. Then we have a move dot word. So we move the word that is at address 80. So 80 has got an address in it. So the contents of that address, so the 2 bytes, and we move them to the address which is held in A1. So those 2 bytes move into the address that is represented by A1. The next one is clear.w or clear.word, and that clears 2 bytes at the address A3. The next one, okay, clear.long, instead of 2 bytes we clear 4 bytes, but it's the same thing. The one next to it, move.long, okay, we moved the contents of the 0, okay, whatever that is in the 0, to the address held in A5. So, and it's a long word, so we are moving a long word, okay? And the last one is similar to the first one, but the opposite way around. So we move dot long the contents of the 0 into A5, okay? Now, we jump to another addressing mode, which is post increment and pre-increment. What does this mean? So it is the same. For now, forget the plus and the minus. It is the same as we were talking before. Okay, so whatever is held in the address, we go and change at that address. So 80, it points to location 1. We go at location 1, and we change or do something at that location. The first one, move.long 80, okay, the contents of 80, and then there we have the plus sign. What it means is, okay, move the content. So let's say 80, and I'm going to bring my notes, so maybe it makes more sense to you, and you can see it like that. I'm not sure if you can see it because my notes are quite small and you cannot make them bigger. Thanks, Crane. If 80 holds 1000, okay, what will happen is 80, after the contents have been read or modified, whatever, because this instruction can be at the source or at the destination, is incremented. So 80 from 1000 ends to be 1004, okay? While if we have a minus first, 80, so the increment happens after the copy or the manipulation of the data, okay? So the plus sign happens, that's why it is after the bracket. The minus happens before. So actually, if A0 is 1000, we get address 996. and we work, it's a long word, okay? So we work from address 996 to address 999, okay? So 996, 997, 998, 999, that is 4 bytes, and we have a long word, okay? So keep that in mind, that that's why the minus is before and the plus is after, because it's how they are when they are actually actioned. Let's put it this way. So I have another example. If we have CLR clear, basically dot long, and we have a minus, so we are clearing for the 4 long words starting at 996. And if we have clear dot long 80 plus, okay, always post increment. In this case, it is post increment, okay, because we have a plus. This means that it clears the 4 bytes after at 1000, at 1001, at 1002, at 1003, and then 80 is incremented. So 80 becomes 104, okay? So that's I hope you understood this. So here he continues with an example, and this is quite an interesting example. So notice what we have here, okay? So at nonno, okay? I don't know why he mentioned nonno. Nonno means grandpa, by the way. He stored 2 long values, okay, here. Okay, you see the 2 long values. And what he did is we are pointing nonno, we're storing nonno into 80, the address of where nonno is into 80. Then we are reading the contents of 80, so we read 3231020, okay? And once we read it, we store that into the 0, but this is the nice thing about it, we have the plus sign. So 80 now points to this byte, to this long word, sorry, which is 13478. So now when we read the next word, okay, long word, as we do here, okay, we are actually moving the 13478 into the 1, okay? And of course, 80 is incremented, so 80 points to somewhere here now, to address somewhere here. So that's quite interesting. I mean, quite a nice addressing mode. The 68000 has got very good addressing modes compared to the 6502. I mean, I'm not saying the 6502. The 6502 only has got 3 registers, but the addressing modes could have been a little bit better, I think. Some like this would have helped. Some registers like this, not registers, some type of addressing mode like this would have helped. So now he gives an equivalent, okay? So notice move dot long bracket 80, so post increment, okay, with the plus label is the same as doing move dot long 80, okay, into label. So and then we add 4 to 80. So all these instructions, okay, this is what we do in 6502 in a way, okay? All these instructions were added automatically, okay, by just one instruction, okay? So see the power of this, basically. This, and remember, this is a long word, okay? So it should be also notice here we move the long word, but he is doing it quick. So to make an instruction even faster, basically, because the quick instruction is the add. When you see a queue, it's always a quick version of the instruction. That is another thing that the 68000 have. Maybe you can say using like page 0, but not exactly the same thing. It's just to give an equivalent in 6502 of something that is faster. And it's a 4, okay? It's a hash 4, so you don't need to use more. 280. And then he continues to give the same equivalent, okay? So he covers all these, but the same thing. Instead of using .long, we are using .word, and if we are using .word, then it's an immediate 2, okay? And a quick of 2, and then if it's a .byte, then it's an immediate of 1. So that's a way of being faster on the 68000 instead of doing that using that type of addressing mode. Now, this routine, you will use it, or you will come across it quite a lot, and not necessarily with the same addresses, but quite a lot on the 68000. If you're creating, wow, I could not, my tongue could not turn. If you are clearing the screen, okay, this is how you clear the screen most of the time, okay? Or, I mean, if you're using the CPU, you can use the blitter also to clear the screen, but right now we're clearing the screen using the CPU. So imagine these were the addresses of our screen. This is the start, where the screen starts, and this is where it ends, okay? -1, of course. So we load the first address of the start address into 80. We load the end address into A1, okay? And then we clear, okay? Remember, we are clearing 4 bytes each time, okay? And we clear 4 bytes and we increment A0 by 4, okay? Remember, that's why we have the plus sign. Then we compare that A0, okay, matches A1, okay? If it matches, then we don't need to continue to clear the screen. If not, we continue to clear the screen. That's all. But this type of routine, you're going to use it. It's quite a common routine in 68000. I mean, in the Amiga, many people probably will use the blitter to do such a thing also. But it depends. Maybe, I mean, I do not know Atari ST, okay? But and as far as I know, the Atari ST did not have a blitter. So definitely clearing the screen was done with the CPU. Let's say that, unless there's something that I do not know. But yeah, or the Apple. No, there's the Apple that had got 68,000, if not mistaken. So it's the same thing. So let's go to our Amiga and do example 2F. Let's see that I am, yeah. So I need to change to 2F. Okay, I loaded the examples already today, so I do not need to waste time in loading the examples. And I'm also timing myself in terms of the examples. Roughly each example will take half an hour, but we have 6 examples, but 2 of them should be done at the same time, basically. So we should still be fine. So in this example, okay, he is, if you see, he has start and the end. So what is start and the end? So he has introduced 2 assembler directives, okay, which is DCB, okay, define constant block. So here we have defined a block of 40 bytes, okay, because we are saying byte here, that contain FE, sorry, okay, so each byte will contain FE. And then we defined a block of 10 bytes, okay, that contain 0. And I'm just going to check one thing with the book, just to make sure that I didn't modify this example myself when I was doing my when I was going through it, because this is something that I didn't envision. I didn't think of. No, but I'm agreeing. It's the same. is the same one. Okay, so 40 FE and 10 10,0. So that's perfect. So I think I need to still look at my notes because there's something that I need to do on the assembler. But you don't need to see it. I can show it to you. Okay, so yeah, so basically this program is very similar to what we did in the book. So the previous example where we cleared the memory. Okay, so what we are doing here is we are loading this where the address of start into 80, the address of the end into 80, A1, sorry. Then we are clearing it, okay? So you can see we are clearing, okay? We're clearing a long word, okay? And incrementing 80, and then we compare, okay, that 80 is to A1, and if not, we branch to the loop. If not, we return, okay? And this, we should see that this block has got, these 40 bytes has got FE into them. And what he wants us to do here is to show us what happens, okay? He told us to assemble, okay? And then do M, and it was start, okay? So we're going to see 40 bytes of FE, and then we should see 10 bytes of 0 at least, okay, if not more, but that is to make sure it's an indication where we end, okay? So you can see we have cleared the, so that is our what we have done with define constant block and define constant block. Just one thing before I continue. Actually, I will cover it later. I will cover it later. I will show you in DefPack and in as-in-one the definition of these, okay? Because there are also variants, so that's why I want to show you that. So with it, I showed you the memory. So now if I do the initio, okay, initio, where the source is, okay. So this is our source, okay. Of course, the labels were converted into addresses, and you can see we are loading 401.88.880, which is the address here of the first where where this start is, okay, and here is the end, okay. So then 401.88 AC8, okay, is the end. This is where our code will end. And then he says to execute it. So I'm going to go back and assemble it. Okay, so now we assembled the program. So now if we do the init, yeah. Okay, so now notice that we cleared that memory, okay, that memory area. Of course, there are also the 10 bytes that we cleared, including that. So we cleared till AC8. So AC8, where is AC8? AC8, we cleared till here, okay. So these are the 10 bytes that, or 16 actually, right? 1, 2, 3, 4, 4 times 12. Why 12? If it's 10. Was it 10 decimal or 10 hex? I cannot remember if it was 10 decimal or 10 hex. in the code. But anyway, you got the point. We cleared that part of the memory as the code shows. So he always, he also wants us to do m start, which you can also see that we have the 0, the memory initialized to 0, okay, till we find after the 10 bytes that we cleared the other numbers, as you can see there. So both when you do an instruction, when you tell the assembler to do an M or a D, you will see the same thing, but one is showing the instructions and the other one is just the contents of memory, just to keep that in mind. Okay, if I do the command AD, so but here he's going to show you how to use the assembler basically. Okay, and I need to move this so that you see it. Okay, so here are all the registers. Okay, so if you press the right arrow, okay, I will start executing one instruction at a time. Okay, and that is what he's saying. He's telling us in the book further down. So you can see me. So we're going to start do an LEA start comma 80. So you will see that 80 has got the address loaded, and then you will see that LEA A1 will have the end address, and then that we start clearing the memory, and I'm executing. You see, I'm looping through this loop by pressing the right arrow, okay, on the keyboard. So it's quite easy to debug in a way using this assembler. Now, what I need to tell you, I think he mentioned it later on, and I'm going to see if it's the next one. Yes, actually, it's the next comment in the book. So what he says is, I'm going to bring the book. What he says here, okay, and I made it in red so that you can to show its importance. When using the debugger, okay, if you are using the hardware, you're programming the hardware directly, okay, it's a bit of an issue using the debugger, and I tell you why. Normally, you switch off the OS, and you are going to see it from chapter 3. We switch off the OS. So if we switch off the OS, okay, the debugger will stop working. Why? Because the debugger uses interrupts and other stuff, and it cannot work unless the OS is there, okay? So I will cover other methods of how the book doesn't cover them. I will cover other methods of how you can maybe debug code, but it's a bit hard when programming the hardware directly to debug your code. Of course, you can always skip disable the OS. Okay, so that's a quick, easy way by by jumping that and then see what the code is doing. But if you want to check something on the screen that is moving a shader, that's going to be tough. But if you want to check something, what's happening in memory, then that's the way to do it. So keep that in mind, that it's very difficult to use the debugger for debugging code that is disabling the OS, which we will be doing because we need the full power of the Amiga. So yeah, let's see if he mentioned something else. Okay, so I wanted to cover that, and there you go. So defpack and as in one. Okay, so define constant block, okay, takes, as you can see it, takes an expression, takes a number, takes something, and then takes another expression. So this is an up. So let's say we put 40, okay, and then as we did here, and then we put the value, okay. Here is the value that we're going to put, FE. So this is define constant block. But there is also another one called define storage, which is the same like constant block, but it initializes the memory to 0. And it also takes .b, .w, and .l, okay? But .word is the default, as you can see for both, okay? The same thing is in defpack, okay? You can see defpack define constant block, okay? And it has .byte, .word, and .long, okay? And there is, because I started from the bottom, define constant, but there is define storage, okay? So here you're defining a block of memory, but not initializing it. It initializes it set to 0. So it says here, these will serve memory locations and the contents will be initialized to 0, okay? Just to make you aware of these two different DS and DCB, not to confuse them. What is the difference between them? You can use DCB, you can use define constant block always instead of using the S, because you can specify the range and the value of 0 basically. So you can do that too. Let's see what else it tells us in the book. I think we jumped into G. Yeah. So there you go. He here defines a define constant block of 80. So instead of 40 as we had before, he defines 80 and put FE. So the same thing. You can experiment with it. I suggest that you download the code, the sources, I mean the book and the sources, and start experimenting with the code, okay? Modify the code as you wish. I can assure you that you will do so when you see chapter 3, when you start seeing something on the screen and something that is, let's say, nice. Okay, so we did that one. So now he's going to cover, okay, here we did a plus, okay? So now clearing the memory, but the opposite way around. But first he gives the same example with nonno, okay? Notice where nonno is, okay? Nonno is behind after this define constant long, okay? So, and we are using the decrement, okay, of this addressing mode, okay? So what we do here is we load nonno, okay? We load the address of this into 80. However, because we have a minus, okay, we are actually loading into the 0 this byte, this long word, okay? So we decrement 80, so we decrement it by 4. So imagine nonno moved somewhere up here, okay, at line number 6, okay? And now we are going to read the long word that is at nonno, which is this 1, 2, 3, 4, 5, 6, 7, 8, okay? So I hope that this makes sense the way I explained it. Yeah. And yeah, today is RamJam, Ozzy. Yes. WinUAE debugger is one of the nice options that you can use, but you can use other stuff like HRTmon, which I find it more better than the WinUAE debugger. But yeah, and there are other ways. You can also have, instead of HRTmon, by the way, is part also of WinUAE, so it comes built in into WinUAE by pressing page up. If you press page up, you enter HRT1. Okay. You can, if you want, you can use actually replay also instead of HRT1. But if your configuration is an A1200, actually replay doesn't work. Actually replay works only with A500 or A600, I think. You cannot use the actual replay. If you have the ROM for the actual replay, you cannot use it if your configuration is an Amiga 1200 or 4000 or one of the others. So I use a HRT1 because it's built in into WinUAE, and you just press page up instead of Shift F12 for the debugger of WinUAE. But yeah, whichever you prefer. I think HRT1 also has more instructions. I mean, it has more options, not instructions, more options, like finding pages, music, and all that stuff. So finding images, sorry, sprites, and all those things. While the debugger, I'm not sure it is so advanced, but yeah. I will cover it a bit in the streams, probably more in the stream of Friday than this one, because the book doesn't cover this one. So I'm trying to on Sunday I'm trying to follow as much as the book, but on Friday I can go my way, because if I do HRT1 on a Sunday, there will be no record of it in terms of it in the book. So yeah, that's the main reason. But we can use it if needs be. We can use it. But if I have to cover it, I think it will be on a Friday more than on a Sunday. That's the only thing, and it makes more sense also. I think the examples here, I mean, there's nothing to debug. They already work, no. But my sources or Phase 101 sources, they do have bugs in them, so it makes more sense to use HRT1 on a Friday. But yeah, it's on my list. Sinlao, thanks for the follow. Actually, thanks for the hosting. Wow, thanks. You're the first one, I think, hosting my stream. Anyway, so then he continues. So like we did with the plus, with the post increment, we are going to do with the pre-increment. So notice that for this instruction move.long pre-increment of 80 into label, this is the same as I just covered previously for the post increment, but we are doing a subtraction instead of an addition. And because we are moving a long word, we are doing for the same thing. If we are doing a word, we are doing 2, and if we are doing a sub of 1, move.byte, we are doing a sub of a 1. So we did that. Now he's going to cover the same clearing the memory, okay, but the opposite way around. So we start with the end where we want to clear, and we go to the bottom, okay, where the start is. When I say bottom, to the start. So this is the end, this is the start, and we use the pre-decrement, okay, and then we compare A0 to A1. If they are not equal, we loop. If not, we are ready. And now we have two examples, actually, the G and then H, which I'm going to cover. How I am with time? Yeah, I'm fine. So let's jump, exit the debugger first of all, and let's jump into the next example. So we're going to do the same thing, but notice start and end where they are, okay, from the previous one. Here we are, same thing, putting the address of the end now, so here, okay, where these 10 bytes start, into 80, and then the start, so we swap these two basically into A1, and then we clear the memory, we compare, if not, we loop again, if not, we exit, we return back to the system. And that's basically it. I mean, there's not much to see. We can do start, and we can see that the memory is also cleared, the 40 bytes that we till we find you see that's where till where we are cleared. But remember, 10 bytes of them are 10 bytes are this block, okay. It's there to show us where we ended. Basically, it's just a precaution. For this exercise, there isn't much. That's basically the same thing like the book. So the next one, okay. So here he is, I just want to jump in the book. So this one is our famous program that we did with the colors, but modified and improved. So he's always improving on that example that we had in chapter 1. Okay, of course, nothing spectacular till chapter 3, but yeah. So basically, if we assemble this and we run it, okay, so we have the same effect as we had in chapter 1, and pressing the left mouse button we exit from it, same thing. The only thing is the speed. This is a lot faster, okay, because we are loading everything. We're using the address registers, okay. We're loading everything into the address registers, and we are performing our loop using the address registers of the 68,000. So we are moving what's in VH POSR, okay, our register, custom register, custom chip register that tells us where the raster line is, into 80. We are moving the address of our color index 0 into A1, and we're moving the mouse address where we check for the mouse into A2. So then when we check for the mouse, just to start from here, okay, it's it's a lot faster than comparing to an address in memory, okay. And the same thing, okay. So that's basically it. I'm just going to check my notes to see if I wrote anything. Yeah. So yeah, it's the same thing. Nothing nothing out of this world. Notice that we are A1, okay. We are decrementing A1, okay. Um, just not to be confused. This is so that the color, okay, we are decrementing what is in A1. So remember, A1 points to DFF 180. So whatever is in A1, okay, the address, which is whatever is in DFF 180, okay. Remember, the address register, the custom registers are where we are decrementing the value by 1, okay. So that's basically it. That's how he's managing to did I say something? So he's adding, he's moving what's in A0 into A1. Yeah. Here it is. Sorry. And then incrementing it. Yeah. And then he's decrementing it again. So basically, we stay at the same. We always, so it goes to df. So that's what I in fact he mentions it here. So this one goes to dff, so index 1, okay, index color index 1, because we were at color index 0. So this one goes at dff 182, but actually when we move, we are going back to dff 180. So this is what he wanted to show also, that we are incrementing the address bar, but then we are decrementing it again. I believe that I did, and that is actually covered. That is actually covered here. He's saying that is like doing that basically. So yeah. So we need to do the next example, I assume. No, we had to do G and H. So G and H. Yes, we did that. So now we're going to see another addressing mode, okay, of the 68,000. This is also quite a handy one. It's quite similar to the having an X or Y register to the address, but remember we have source and destination in the 68,000. So it is this type of instruction. Let me see if I manage to highlight it. It's not letting me for some reason. So it is, I hope you can see my, yeah, okay, there you go. So that's the type of instruction addressing mode that we are going to cover now, and it is called register indirect with displacement. So basically what we do is we take the contents of A0, okay, as we were doing before, but we also add the value that we have outside the bracket, which is the 100, okay. So if A0, and I'm going to bring my notes now, okay, I hope you can see them, you can read them. It's not that I can make them bigger. So if A0 contained 6,200, okay, then if we have a 60,000, okay, and we have 100 at before the bracket of the 80, okay, then 80 becomes 6,300, okay. If we had minus 100, so somewhere here, there you go. So he mentions the minus, okay. If we had minus 100 instead of plus 100, then instead of come on, show up. Does it want to show up? Okay, so then instead of 6,200, we end up with 6,100 because we have minus 100. So it's a very easy addressing mode to know and understand, okay. So basically, I mean, it's best demonstrated with the example, with the next example, which is I, okay. But not much. It makes sense, okay, that what is outside the bracket is added or subtracted from the value that is in A0, okay, from the address value that is in A0. Please note that that value can be, so it's a 16-bit value, okay, so it can be minus 32768 and plus 32767, okay. That's how much you can displace on the 68,000, which is quite a lot if you think about it. It's 32K. Okay, so let's pass to example 2i. Okay, so I think F3, F4, there you go. So this example, okay, we have the base address register, okay, where the custom chip starts, okay. I'm just going to see, check my notes just in case I am, just in case I'm going to miss something more than anything else. So this is a clear example of using this addressing mode. So we loaded the base address, okay, of our custom chip register, where the custom chip register, the first one is for our custom chips, which is DFF00, and we load that into 80, okay? Then, remember, VPOS is at address 6, DFF006. And colored 0, just to remind you, I can go one back. I need to have the mouse pointer here to press. So, and I need to go page up. Remember, so base address is DFF000, but now we have 6, okay? And this one we have 180. So, look what he did. So this is even a neater way of improving on our example, okay, that we had in chapter 1. So 6, we are loading the same address, okay, DFF006, okay, into DFF180, because 80 in both cases contains the base address, and we are adding 6 or 180 to it. Then we are testing for the mouse button, okay? If it's pressed, we exit. If not, we loop. And it's the same thing. So if I execute it, so this is the beauty of the examples in the book, that they are so constructive, one on top of the other, and so easy to understand. So you see, we have the same effect, okay, but using the addressing mode that he building on the first example, using the addressing modes. So nothing special in terms of an example. It's more understanding the addressing modes. I'm just going to continue to see his notes to see if I'm skipping something. Yeah, so this is one way of how we do it. Basically, you load the address of the custom chips in one of the address registers, and then you work offset to that. So yeah, it's quite a neat way of addressing the address registers. Sorry, not address registers, of addressing the custom chip registers. Okay. I'm just seeing that he has a note, so I'm just going to go down into the example. So he has a note somewhere here. Yeah. So basically here he's going to talk again about the difference between LEA and move. Okay. So here he has here he has a move.long 100 into and 80 into A1, and here we have the same type of instruction but using LEA. One is moving the contents of, okay, and the other one is actually moving the address. So if 80, okay, had 60. How can I show you my example, my note? Let's see if my notes will show up. Yeah. There you go. So if I don't touch the mouse, it should stay there. So, oh, wrote LEA wrongly. I wrote it lean. I had an extra N. Anyway, typo, which we'll fix. So if 80 has got 62,000, okay, so move long 100 bracket 80, comma A1, okay, that means move the A1, move the contents of address 80, of address 100 plus 80. So we are moving the contents of 63,000. No, I have even another mistake. That should have been 1,000, that number. So imagine instead of 100, I have 1,000, okay? Because I entered 100 there, but it should have been a 1,000. So then the contents of 80 will be moving to is even down, even further down. I'm noticing that I made a mistake. My God, I shouldn't be showing you the notes right now for the typos that I have. But anyway, it's not a big deal. You understand what I mean. Instead of having 100, put 1,000 there. So A1, okay, will load the contents, okay? Remember, we're going to load the contents into A1 of 63,000, 63,001, 63,002, 63,003, okay? While if we had LEA, okay, and again, 1,000, not 100, okay? Then A1 will contain the address of 63,000. So one, we are loading the contents of. The other one, we are actually loading the address. Okay, we are doing an addition of what's in 80 plus the 100, the one, sorry, not the 100, the 1,000, and that addition is what goes into A1. Just to notice the difference, okay? He doesn't give the answers to that actually. Yeah, he doesn't. So that's all the text, and then I should have another one here. You can also write the displacement. You can also, I write it as an expression, okay? So right now he has 16 or 10 times 3, okay? And add it to A1, okay? So you can put expressions there, and it's fine for the assembler. It will convert that number into whatever the expression results to, okay? Okay, so far so good from what I see. Just let me know if there are issues. Just I'm concerned after last Friday. So let's continue. So we did 2i. Okay, we are going to do another addressing mode, and this is where the beauty of the 68,000 come in. So we did 100 and an address register, but imagine having 100, okay, an address register and a data register, which we have here, okay? Look, we have the 50 here, we have the address register, and we also specify a data register. Both combined, we get the value that we need. Sometimes you need this, okay, on the 68,000. So it's quite a handy and quite an advanced addressing mode. and quite a useful one too. Also note that the displacement, the d0, can only be, so the displacement is short, okay? Can only be to -128 to 127. But it does the job, okay? Before I continue, I just want to show you something that the document of the 68,000 shows. So this document, which I shared with you some streams ago, I think in stream number 2, which you can find in my Discord. By the way, all the links, you can find them in my Discord, okay? They are there. The addressing modes, okay, those were, the way he's showing them there is the old way of doing the addressing mode, which the assemblers still understand. So to be honest, I use the old addressing modes. Sometimes I switch to the new ones, but I use the old. But the new addressing mode has changed a bit. So notice the D, the displacement, is outside, while in the current notation, okay, it's inside. Okay, so for both of them, you know, the displacement is inside. There is also displacement with program counter, which, as I said, I am not covering this, but in chapter 3 he will mention it. Okay, the book skips the addressing mode related to the program counter, and he did it for a good reason actually, because you will you can get confused. So it's better for now to stick to the these addressing modes. But I wanted to show you the writing of the old notation and the new notation. So that is the displacement is this one, eh? So the displacement is +128 -128. So you have full addressing mode, full addresses in both cases. Okay. So let's see what we do here. Okay, so that was for the addressing modes, but to be honest, there's still the example, but I'm just going to talk about something else, which the book covers, which is related to the addressing modes that we just covered, and it's good that you know. So the 68,000 has got an instruction called decrement and branch, or the modern way of DBF, decrement and if false, okay, which I'm going to show you also. So instead of, so decrement CC can be replaced. There's lots of different ways of checking on the 68,000, okay, and one of them is by adding an F, which is false, or you can add a T if true, okay. But the old way, actually it's not the old way. Somebody told me last Friday that this is the old way, how we used to do it. I looked it up actually, and I found out that it's a way of, you can still use, in fact it says it here, no, that many assemblers permit the mnemonic DBF to be expressed as decrement and branch, which to me, decrement and branch makes more sense than DBF, but it's a way of, it's a matter of preference, more than anything else. You can use DBF. I remember in the old days using DBF, and actually I saw some source with DBF, and then I saw some sources with DBRA. So it all depends from all this, from your preference basically. Just know that you can use both. Also, I forgot from where I got this. I need to find the link. I found the 68000 Motorola Programmer's Reference Manual, which the reason why I have it is because this one covers, and I'm going to show it. Maybe there's a page where it shows it, this one. It covers all the 68000 CPUs plus FPUs till 68040. There's no 68060 in this book. There's a separate book, I believe, for the 68060. But personally, I do not consider an Amiga with a 68060 a good choice. Personally, I mean, probably people will tell me, "Oh, what are you saying? 68060 is a lot faster." Yeah, but most of the software doesn't work. So this is why I don't like the 68060. Not because it's not better. It's a better CPU, yes, but the software was not written to cater for it. But there's lots of software that fails with the 68060. So you can have 100 megahertz 68060, but I think there's lots of software that fails with it. And in fact, I only use till the 68030 more than the 68040, because even with the 68040, there's some software that fails. In fact, my A4000 is 68030. I had the choice of having a 68040, and I went for the 68030 because of that. Because I know that it will not give me problems with the 68030, but it will give me problems with the 68040. This is, as I said, a matter of preference more than anything. But yeah, look for this book. Try to find it out. I forgot from where I found it. If somebody finds the link, please share it. I did have this for quite a long time, so that's why but it's called Programmer's Reference Manual. Okay, for the 68 by Motorola. I have version 1 here. I don't know if there are other versions of it, but make sure that the name matches, because there are others and they are specific to the timings and all that stuff. Which I do have also, but for the instruction set, that's the book that you need. So what he's covering here, notice that we are loading the address 60,000, okay, into 80, okay. Then we are loading into the 0 an expression which is 2000, so we are going to clear 2000, but because we're doing a long word, so we are dividing 2000 by 4, okay. And then we are also decrementing the result of that by 1, because remember we start from 0. So if we do the result till the end, we will be clearing an extra memory location, actually a long word, 4 bytes. So this is why we need to do -1, and we move that into the 0, okay. Then we clear what's in a 0, okay, and we decrement the 0, so we decrement the value that we have in the 0, and if it is not 0, so that's what it is, decrement and branch if the 0 is not 0 or false, okay, decrement and branch if the 0 is not 0 but the f false, so it is false, no, it is not 0, so we go back to clear loop and we continue doing that basically. So that is all. Let me see if in my notes I had anything that I have skipped. So yeah, here imagine we have a branch, a BNE, branch or not equal, okay, hidden. So that's why we are doing. So basically on D0 we have a check on D0 to see if it is equal to 0 or not. If it's not, we go and do the loop. Okay, so here it's going to show the examples. This is 2L. Okay, so we're going to go to 2L. So let's go to the assembler and we set 2L. So L, there you go. Okay, so here he's going to give examples, okay, of decrement and branch, or branch or not equal. This is because branch instructions are very important in 68,000. There are a lot of branch instructions in the 68,000. We are just touching one of them basically. The rest will come as we go along in the book. But if I had to show you again, I mean, if I remember, I will do it in the book, the 68,000 reference book. All the branch instructions are there, and I can show them to you. I think there are 14 of them compared to the 68 to the 6502. I can't remember exactly. Maybe a bit less, maybe a bit more. But yeah. So what we are doing here, first of all, he is showing the branch to subroutine. Branch to subroutine is not jump to subroutine, okay? Jump to subroutine can jump anywhere in memory, okay? Branch to subroutine can only jump in a range of 32K, basically. 32768 or plus 327, minus 32768 and plus 32767, okay? So keep that in mind, but it does the same thing like a jump to subroutine, which is it looks for the RTS instruction, return, and returns back to the code. So here we have two. So in both cases, we are jumping to lampeggio or branch to subroutine caler freccia, okay? Whatever he wants to mean by that. So it is here. So we are jumping the first branch. We are jumping to caler freccia. The first branch we're jumping to lampeggio, which is further down, which is this, okay? And the other one, freccia, we are jumping here. Both of them has got an RTS. So this is one subroutine till here, and this is one subroutine till here, okay? This subroutine has decrement and branch, okay? So we jump into it, we do something, and then we return, okay? While here, we execute one after the other, and we return, okay? So that's the difference between the two in terms of instructions. So what are my notes in relation to that? So he is using where he has, I think I'm hiding one instruction. No. So, here, that's the one. Branch on not equal, okay? Non premuto, okay? Which means it was not pressed, okay? So non premuto is somewhere down into the code, I guess. Non premuto. Here. Okay. So if something was not pressed, okay, for now, let's do that. If something is not pressed, we jump to here, okay? If it is pressed, we do fai confusione. Okay, so basically this is also a way to show that you can write spaghetti code if you are not careful, okay? So notice how the jumps are going. It's a way of showing to be careful, not to be careful of how you write code, and not to be jumping in middle of things because you can create confusion. I mean, this is the same in any programming language, I assume, but yeah. Okay, so let's execute the example. So it's doing the same thing as you see, but and I think if I press the right mouse button, now the mouse pointer will flash. I need to, because if I remember correctly, okay. Actually, the mouse pointer, not the red, the other colors are actually flashing. Um, yeah, so I think it's very difficult for you to see it. It's very difficult to see. It's very difficult to see. Anyway, let's see what this code does. Okay. So we're moving the base address into 80. Okay. Same as before. Print it only you have. It's okay. Then we are moving 20 into LDC bracket 80 beam con 0 ECS plus resolution. I see why my screen was getting smaller. So basically he's changing the, okay, let's get the register to make you aware of what he's doing. I need my web browser and I need this one, and he's talking about 1DC. So let me find the register 1DC. Here. Beam counter control register. Okay. That's the one he's talking about. And he is moving 20 into it. So 32, sorry, because it's hex. So he is moving. So this is the contents of beam con 0, which is 1DC. Okay, so that's the register he's talking about, and he's moving 20 in it, which is, he's talking about this one, var beam mem. So var beam mem use the comparator generator vertical blank. So this did not exist in OCS, but it exists in ECS to run the internal chip stuff, sending RGB signals to Denise, starting sprites, resetting light pen. It also disables the hard stop of the vertical display window. So that's why, and I'm going to show it to you again, that's why if I pressed it for long, which I didn't do initially, but then I realized if I press the right mouse button for long, so that's what it actually does. The screen will get smaller for a period of time. Okay, that's the main thing. We are, let's say, changing the mode of the screen. That's what he's doing basically. I wonder if I put a note to this on my in my notes. Yeah. Okay, so basically what it actually does, we are switching between PAL and NTSC. But of course, we don't really have a screen, so that is what happens. It's like the screen shrinked completely. So at least this is what I understand. Maybe I'm wrong, but yeah, by changing that bit. Here I have a note that it was bit 5, not bit 7. Let me see again the page. Maybe I said wrongly. Bit 5. What is bit 5? Yeah, actually, we are modifying bit 5, which says PAL or NTC or NTSC. Yeah. So basically, we are switching between PAL and NTSC. Okay. That's why the screen shrank. Once we move 20 into 1DC, we jump into Lampeggio, and Lampeggio we just move, read what is in vposar, okay, the register that has got the raster beam, and we put it in colored 0 and 1. So we are modifying colored 0 and 1. That's why 180 and 182. Okay, index color 0, index color 1. And remember, 80 contains DFF000. Okay, so we did lampeggio. Then we jump to and return back, and then we jump to color freccia. Okay, so now we move FFF. Okay, -1 is FFF. He's mentioning it here. It's not actually, because this is a word, because it's move quick. So it is FFFFF. It's a way of moving 4 FFs into the one, and very quickly, basically. So the one has got FFFF, whatever. And then we move 19, okay, in color freccia. So in the 0, not sure what he's doing here. I remember when he did it. So the 0 points to, does not point to anywhere. No, not yet. So the 0, yeah, I think he's doing something to the color register of 1A4. So 1A4 is what? Okay, so he's playing with another register. That's why I was not understanding. So 1A4. You see, I did this quite some time ago, even my notes. So yeah, color 18. So as I said, he's changing the color of the sprite too. It's just that for you guys, it's difficult to see. It's difficult for you to know that the I don't know if how I can zoom on the mouse, but yeah, that is what he's doing. So basically, he is using register color register 18 for the sprite. So he's changing one of the colors for the sprite. So this one, 1A4, is, just to repeat it again, is color 18, color index 18, which is color number 2, no, for the sprite, if I'm not mistaken, by heart. Now, move quick is not actually a word. It can only be a byte. But the most significant bit 7, is echoed on all others. So it becomes a long word. Okay, and I think this is something that I covered last week. If I find the book, I'm just going to find it to show you what I meant. Move quick. Where does it say it? So here. You see, consequently, although only 8 bits are moved, the move quick instruction is a long word operation. So the most significant bit is echoed on all other bits when you do -1 to 8, right? That's what he did, if I'm not mistaken. Yeah, -1 when you do -1. So yeah, that's the way it works. Yes, but it's an internal one. So the CPU is coded to do that. So yes, it's a long word um, into the one in that case. Yes. Um, so yes, it's a 32-bit operation. But when you are, if you do move quick one, okay, note that you are moving either a word or a long word, and most of the time it's a long word. If I remember, actually, it's always a long word. Sorry, it's always a long word. In fact, um, I thought it takes .w, but look, size is always long word. Okay, so that is that clears it up and shows it better um, what it is saying, what he's saying. Okay, so we do we change color 18, okay, and we decrement the values, okay, and with flash. So this is where we are actually doing something on the mouse pointer, and we decrement it from 19 to 0 um, by and then we move that value into into the color register related to the sprite. It's a very it's more of demonstrating decrement and branch more than actually you can see something. It's very yes. If you do move quick 0, comma the 0, you're actually using a long word, so you're clearing the register. Yes, it's faster than CLR. So yes, and the same thing if you do -1. If you want to move FFFF, it's for 8Fs basically. Um, it's the same thing. So it's a quite a nice feature of move quick. Well, that's why it is called move quick, no? So then after we did lampeggio, okay, we check non premuto. So did we press anything? Um, Nothing was pressed. It's so we skip this instruction. So basically, it's just a test to skip this instruction. Fai confusione, which means make confusion, and that's what also is something that he's trying to tell us to avoid. Okay, to avoid confusion. Then um, we avoided the confusion. Then we do actually the test. Okay, the test for the left mouse button, and if it's pressed, okay, we exit the program as we continue to loop. Okay, so that's basically it. He wants that we do I can show it actually. He wants that I do a D, okay, and like that you can see me executing the instructions. I'm going to do it for a little bit. So we jump there, we return, then we're going to jump to freccia, and we loop basically in color freccia. Okay, we're going to do this for 19 times, which is annoying, doing looping like that. So we are decrementing at the same time the 0. So notice the 0 is 5, 4, 3, 2, 1. And now we should exit. Okay? Boom. And then we return to the test and we continue like that. So that's basically it. Let me see more of my notes. What he says. He's explaining branch on not equal and branch on equal. Basically, imagine a tree where you have branches and it depends on the branch. You either go in one direction or the other. And actually, he shows us this with something like here. Look. So this is the part that he says where he says we are checking for bit 5 of DFF1DC, and it switches between PAL and NTSC, but it's not available on the old chipset from what I can tell. Okay, last bit of the example, right? Yeah. He's explaining that if you want to save the program for NTSC, you save the program by having bit 0 in DFF move word 0 DFF1DC, okay? Or move word 20 is NTSC. So this is PAL with 0 and 20 is with NTSC. And basically you can do 2 programs to switch your Amiga. That is actually what he's saying. You can write 2 programs just with this one line, okay, and RTS, and the same thing here, and you can one call it PAL and one call it NTSC, and you can switch the Amiga from PAL to NTSC and vice versa. It's a quite handy trick actually that he covers. Okay, let's continue with the book. Here is actually the program that we just similar to the program that we just did, but he's just showing BSR. So these things are dummies, okay? It's not really something doing something happening there, but just to show branch to subroutine and compare and branch are not equal, and we are jumping here sottoposto. So sottoposto, we are jumping here. Once we find the RTS, we jump back, then we continue doing something with the code, and compare something, and according to the compare we branch to if it's equal to we branch to strada 2, and if not we do this. Okay, so it's just a way of showing branch on not equal and branch on equal and branch to subroutine. It's something that we covered already. He just likes to repeat things because it does help when you are a beginner. We are checking for the flag. You know, the 68000 has got a status register, and we are checking for the flag, for the 0 flag, whether it's set or not. When it is set, then it is not cleared, so it's not equal to 0. When it is cleared, it is 0. Oh, did I say it correctly? When it is 0, it is a 1. Sorry, when it is at 0, it's a 1, so branch on equal. When it is not 0, it is 0. It is not set. So here he explains the difference between branch, BRA, and jump. Like we have for jump to subroutine, and we have branch to subroutine. So one is able to address the full memory and the other one doesn't. It's only able to address jump into a range of 32K, basically. Plus or minus, so 64K in total offset. We have the same thing for branch and jump. Jump can jump anywhere in memory, okay? But branch can only jump within your code. Normally within your code you use branch, and outside your code you use jump. Same for JSR and BSR. In your code, because your code normally is not so long, you will not write a routine which is long 32K. You will use BSR. If you want to call something outside like the system libraries, you use jump to subroutine JSR. Okay, so that's mainly it. So we arrived to the last example, I believe, to M. So let's jump to the Amiga. And we need M. Okay. So here he's showing, okay, that working on address registers 80 to SM, you are always working in long words, even if you use .w. Yes. Address registers only work on, I mean, an address cannot be a .w, okay? Cannot be a word. An address can only be a long, okay? So you are always working on long addresses. That's an important point to know. So when you are working with data registers, you can have byte, word, and long word. But when you are working with address registers, it's always a long word. So that's the first thing to note. It's a good note that he did in the book. I think he wrote it somewhere up here. Yeah, yeah. Then, because we are using data registers here, so this is what he wants to demonstrate when using address registers and data registers. Because we are using data register, okay, we are moving .l, okay, into the 0. So we are moving a long word into the 0. Here, we are using .w, okay. Now this goes into contradiction of what I said before to Ozzy, but think of it as we are working on data now, not on address, okay. We are moving 4, so 4 is smaller than those, either a 0 or an 1 to a minus 1, okay. So even though we have .w, okay, so remember I told Ozzy that it's always long word, and actually, and you don't need to specify .w. So here, even though we are writing .w, even what he says here, okay, if you can translate it, it will always be a long word, okay? It will always be a long word. Okay, so here we are just modifying 2 bytes in the 0, but here we are modifying 4 bytes. Okay, I hope this makes it clear. The address bus of the 68,000 is 24 bits, but on the 68020 upwards it is 32 bit. You have 32 lines, but when you address something, it's always a 32-bit address. You don't, I mean, you get the first 2 or 1 nibble, which is always at 0, basically. So that's what happens on the 68,000. If you have a 68020, it's full addressing full 32-bit lines. Yes, as in Pro is intelligent to change those. Yes, so that's why if you do .w, it will change it internally into .l. No, not the CPU. It's the assembler that is doing that. The CPU cannot understand you. The CPU just execute instructions. It's the assembler that changes it into what the CPU can understand. So yeah, it's the assembler. They are in the assemblers of the 68,000 are quite optimized. They do change code. I think by default they have some levels of optimization. You can specify it. So Yeah. No, the assembler won't give you an error. It will optimize it. Um, it's by default, I think. Um, I hope that you are enjoying this series, and trust me, from next chapter the fun begins. You will start seeing graphics, and by the end of chapter 3 you will see some good graphics, good things that you would never thought it is so easy to do them. Um, when I did, I mean, this is a long time now. When I did chapter 3, I just was impressed with the book there. I mean, in the first two chapters, I found it boring, maybe like you guys. In terms, it's a long, winded way till you arrive to chapter 3. But especially because the examples are also very long. But when I started working on the examples, holy crap, it was a big difference. It was really fun. So I do, for those that are sticking with this, I do recommend you to join when I start chapter 3, and follow, because we will be programming the copper, and you will see copper bars and all that stuff, just to give you things. But we will do even more than that with the copper, which is quite fantastic. He will show some tricks like zooming in with the copper and stuff like that, which is incredible. So yeah. Anyway, just to give you a bit heads up what's coming in chapter 3, and also, if you like what you see, please follow this stream. I really would like to reach, um, my target is 100, but yeah. Anyway, but thank you anyway for the follow so far. Let me see if I have more notes. He says to use debug. So okay, and we go through it to understand exactly what's going to happen. Okay, so I should have used AD, sorry. Okay, so let's see what's going to happen. So the first one, we're moving the value into the 0. So the 0 is going to be FFF. Then look what's going to happen to the 0 when we move D4. Okay, remember we have add quick.w. Look what happened with the 0 now when we did add quick 4 comma the 0. You see the FFF, the word, okay, this word here, remember it was FFF, we added 4 to it and it turned into 0003. Okay, so that is something to keep in mind. Okay, so we affect it only because it's a data register, only the word of it. Okay, but now look what's going to happen, because we're using LEA and an address register. Okay, so we're moving FFF same into 80, so we will have the same value. Okay, we will have the same value. Now add quick 4, see what's going to happen. You see what a big difference. We actually added 4 to the FFFFF. Okay, so that's a big difference compared to when we are so when we work with an address register and the data registers, keep that in mind, and we are using add quick. Okay, when we use the quick version of the commands, even if it was move quick, it's the same thing. If we move quick to an address register, it's always a long. Just keep that in mind, because you can fail on it. I mean, I make this mistake even till today. Okay, so it can happen that you forget. Yeah, so he said that, and we finished the example. So if I finish the example, it means I finished the book too. So as you can see, as soon as I finished, I turned into chapter number 3. So the first example is that one for chapter number 3. I do suggest that you download. From now on, you will need the examples. You will need the examples even for you to learn more, to look at. So I do suggest that you download the book with the examples. Okay, the examples, when they transfer them from Amiga to PC, there were some code, not code, some things that didn't transfer. But I will tell you, it's not a big thing what didn't transfer. So you might try to execute some examples just to make you aware. Let's say in chapter 4 especially, you try to execute some examples in chapter 4 and they won't execute. That's because there are some things missing, which I will give you. I mean, I will share with you. Um, but when we arrive at the chapter. So we have finished chapter 2, and also here I should see chapter list, and as you see it's copy list. Okay, so I hope you have enjoyed this stream. I am quite quite a few of you following, so thanks very much. I did not expect to have so many followers. I just want to thank you. I wish you happy Christmas and a happy New Year for those that will not be joining me in the next stream or on Friday. I hope you have a lovely New Year and a lovely Christmas. And I know that this year was difficult year for everyone, including myself, but we do the best of it. And actually, I did. I started these streams, which I'm quite enjoying, especially when I see you guys taking interest. So yeah, thank you very much.